Hi everyone, my name is Yu Wang. I'm a PhD student at NYU Music and Audio Research Lab. I'm going to present active fuchsia learning for sound event detection. This work is collaborated with Mark Cartwright and Juan Pablo Bello. Fuchsia learning has recently been proposed for sound event detection and shown promising results, where a model is trained to learn to recognize novel sound classes unseen during training, given only very few examples from each new class at test time. This framework typically involves a metric-based few-shot model that learns a discriminative embedding space, which is good at generating a robust representation for a novel class based on just a few examples, called the support set. We can then model the non-target class using the entire test recording, assuming the target sound is sparse, or use other existing data where the target sound is not present. With these two representations, given an audio frame, we can do binary classification using nearest neighbor classifier. Here, the support set of the target class is critical for a good representation. One of the main assumptions in a standard few-shot setup is that the human user can provide a few representative examples, for instance, 5 examples. And most research studies simulate this process by sampling the support set randomly and uniformly from all test data with the target class label. However, in reality, users might not even have 5 examples at hand, for example, for a newly emerged sound. Or these examples may be from a limited context and not representative, resulting in model performance lower than expected. In this work, we relax these assumptions to reflect real-world scenarios. We start from just one target example, mimicking the scenario when a user first recognizes a new sound event of interest. And we randomly sample 100 non-target examples from the training set to model the negative class. Typically, it is hard to get a robust representation with just one target example. To recover model performance, we propose to use active learning techniques to efficiently sample additional informative examples at test time. Specifically, we use active sampling to find the most informative example for the model from the entire test set, and query its label to update the support set. In this work, we simulate the human labeling process by directly using the ground truth label. We perform a series of experiments under this framework to explore the modeling and sampling choices that arise when combining active learning and few-shot learning. First, we compare different sampling strategies. Next, we explore different training schemes for the few-shot model. Here, we use the prototypical network. Lastly, we study how different temporal windows in sampling affect model performance and generalization. We run the sampling process 100 times. To perform these experiments in a realistic setup, we create a new dataset, Sonic FSD set, which simulates a year of audio data in an environmental sound monitoring system. It has several properties that are hard to find altogether in an existing dataset. First, it is a large dataset, consists of over 460,000 of 10-second soundscapes, with disjoint sets of classes in different splits. Second, we have perfect annotation, because we programmatically mixed each clip using Scaper by using the recordings collected from an acoustic sensor network in New York City as the background, and sampling foreground sounds from the FSD50K dataset. These datasets also reflect the seasonal periodic patterns of the occurrences and co-occurrences of sound classes, as we model the occurrence probability within a year for each sound class. Also, this dataset will be freely available on Zenodo. In our first experiment, for the sampling strategy, we consider an uncertainty-based sampling, where we use the trained model to find the most uncertain example from the test set. At each iteration, we choose the example with the predicted probability closest to 0.5. For comparison, we also run the same pipeline but sample additional examples using random sampling. At each sampling iteration, we report the mean F measure for performance and mean total positives for sampling efficiency, averaged over 30 test classes. We also show the model performance when we have 5 random positives as assumed in a typical few-shot setup as a baseline. The results first show that active sampling outperforms random sampling at all iterations. Next, we see that while performance drops from the baseline due to relaxing the standard few-shot assumptions, with active sampling, we're able to bring the performance towards the baseline and even go beyond it with increasing sampling iterations. Lastly, we see that active sampling returns more positives at a faster rate. These results indicate that the uncertainty-based sampling strategy is effective at sampling informative and representative examples more efficiently. In the second experiment, we explored different training schemes for prototypical network. In a standard setup, we train a CNN-based backbone via episodic training with 10-way 5-shot classification tasks, where in each training iteration, we randomly sample 10 classes from the Sonic FSD set training set, and for each class, we sample 5 examples into the support set. Then, to classify a query example, we embed both support and query examples into the embedding space to perform nearest neighbor classification and update the model based on the classification laws. In this case, the number of support example per class is a fixed number of 5. It was originally designed to match standard few-shot testing scenario that assumes we have a fixed number of support examples available. However, in our proposed setup, we start with 1 target examples and iteratively increase the number. To further match our testing scenario, we propose 2 new training schemes. First, instead of training with fixed 5-shot, we train with random shots. In each training episode, we randomly choose n between 1 and 20 for each class. By doing so, the model can learn to work with different number of support examples. We call this training scheme the random shot training. Next, we go a step further to match the entire active sampling process. In each training episode, we start from n equals 1 and select an additional 100 samples per class to form a sampling pool. Then we run 100 active sampling iterations to sample the most uncertain example from the pool to update the support set. We compute loss and gradient at each sampling iteration and perform 1 backpropagation after 100 iterations based on the accumulated gradient. The results first show that with random sampling, the random shot model performs significantly better than the 5-shot model, indicating that matching the setup with varying numbers of shots at training is critical for model performance, while the active shot model improves even further, showing that training with more informative support examples using uncertainty sampling results in additional performance boosts. With active sampling, however, we observe a trade-off between performance in few-shot and miss-shot regimes, where no one model dominates both regimes and there is always a cross-point in performance. We plan to investigate further to understand this behavior as part of the future work. Considering the performance in the few-shot regime is particularly important due to lower annotation effort, together with the longer train time for the active shot model, we fixed the training scheme to random shot in the rest of the experiments. In the third experiment, we investigate how different sampling windows affect model performance and generalizability. In addition to the original training and testing data, we generate 2 more years of test data following the same data generation process. For each test class, we find the peak position of its simulated occurrence probability distribution in the current year. Then we define 5 temporal windows, from 2 weeks, 1 month to 1 year, to sample additional support examples, simulating scenarios where we have varying access to the historical data. Finally, we compute performance on the data a year before and after the current peak timestamp to see how the model generalizes to data in the past and future. We consider both random and active sampling strategies, and here different colors represent different sampling windows. The result shows 2 general trends. First, the larger temporal window of sampling results in higher performance, indicating that example diversity is critical for prototypical network. Next, the model performs better on data in the past than on data in the future. This matches our intuition that the model generalizes better to data it has access to during the sampling process. To recap, in this work, we relaxed the common few-shot assumptions that a handful of examples sampled from the entire test sets are available at test time. To recover the performance, we propose to incorporate active learning techniques to effectively sample more examples to update the support set. The experimental results first show that with uncertainty-based active sampling, we can expand the support set more efficiently and achieves better model performance compared to random sampling. Next, we propose 2 new few-shot model training schemes to address varying number of support examples during the active sampling process. Lastly, we show that model performs better with larger temporal window of sampling and on the historical data than on the future data. Also, we create a new public dataset, Sonic FSD set. For more experimental results and other details, please stop by our poster session or check our paper. Thank you.